Welcome to Chapter 12, Fundamentals of Radiation. Today, we're entering a fascinating area of heat transfer, radiation. Unlike conduction and convection, radiation doesn't need any medium to transfer heat. That's how the sun heats the Earth, even through the vacuum of space. In this chapter, you'll learn why all objects emit radiation, how we calculate the energy involved, and what makes blackbody radiation special. We'll also discuss important terms like emissivity, absorptivity, and the Stefan Boltzmann law. By the end of this session, you'll understand why you feel warm near a fire even without touching it. Pure radiation at work. Get ready for a very illuminating session. 1. Focus on practical learning goals. When you start any technical topic, it's helpful to clarify exactly what you'll gain from it. Clear learning outcomes help you stay focused and guide your study. In this chapter, every point connects to a practical skill. You're not just memorizing formulas. You're learning to classify types of radiation, apply powerful laws like Stefan, Boltzmann, and Planck, and understand real-world effects like the greenhouse effect. For example, instead of just knowing about blackbody radiation, you'll be able to calculate how much energy it emits. You'll also connect theory to modern issues like atmospheric radiation. Always study with the outcomes in mind so you can turn knowledge into useful, applicable skills. 2. Explain thermal radiation simply. Students often think of heat as something that flows only through solids or fluids. But radiation changes the game. It doesn't need any material at all. It moves as electromagnetic waves, just like light. A simple way to see this is by thinking of sunlight. There's no air in space, yet Earth stays warm. Why? Because the sun's energy travels through a vacuum using radiation. Instead of memorizing facts, focus on the big idea. Radiation transfers energy across empty space carried by photons, making it crucial in everyday life and natural phenomena. Understanding this helps you explain why you feel the sun's warmth or why infrared heaters work indoors.
3. Link radiation to everyday energy. Radiation is part of the electromagnetic spectrum. And to make it simple, think of it like a big family of waves. Some waves, like X-rays, are super short and carry lots of energy, while others, like radio waves, are long and gentle. All these waves travel at the speed of light, around 300 million meters per second. But what really matters in heat transfer is the thermal radiation part of the spectrum, from 0.1 to 100 micrometers. Here's a tip. Remember this rule of thumb. Short wavelength means high energy, like sharp X-rays, and long wavelength means low energy, like soft radio waves. This helps you quickly predict the behavior of thermal radiation in practical problems.
4. Simplify blackbody concepts with real-world analogies. Blackbody radiation sounds complicated, but think of it this way. A blackbody is like a perfect sponge for radiation. It absorbs everything and re-emits energy at the highest possible rate, with no waste. You'll use 3 key laws to describe it. The Stefan Boltzmann law shows that hotter objects emit more energy, and it grows fast with temperature to the 4th power. Planck's law explains how much energy is emitted at different wavelengths, giving you the shape of the radiation curve. Wien's law is your shortcut. It tells you where that curve peaks based on temperature. Hotter means bluer, colder means redder. Focus on the logic. Blackbody means maximum emission, and these laws help you predict how much, where, and at what wavelengths energy is released. Focus on what each radiation term really means. Students often get lost in radiation terms, so let's simplify. Radiation intensity is about direction, how strong radiation is in a particular direction. Irradiation is about incoming energy on a surface. Radiosity is about outgoing energy, which includes both what's emitted and what's reflected. To make life easier, we use hemispherical relations, basically integrating over all directions above a surface. That's where pi comes in. Think of it like spreading out the directional energy over a whole hemisphere. The key takeaway: don't memorize blindly, understand the role. Direction, I, incoming, G, outgoing, J. Use the pi relations when you need totals from all directions.
6. Break down surface properties into simple rules. Let's simplify surface radiation terms by focusing on what really happens when radiation hits a surface. Part of it is absorbed, absorptivity. Part is reflected, reflectivity. Part may pass through, transmissivity. And part is emitted, emissivity. For most real-world solids, especially metals, transmissivity is 0, so we only split between absorbed and reflected energy. Kirchhoff's law keeps things easy to remember. In thermal equilibrium, what a surface absorbs equals what it emits. So, high absorptivity means high emissivity. This is why black surfaces both absorb and emit well. Always connect these definitions to physical behavior. Ask yourself, is the surface shiny or dull, transparent or opaque, a good absorber or not? That makes these terms practical, not just formulas. 7. Simplify surface types for practical use. When dealing with real surfaces, things get messy, so we use simplifications. A gray surface means its emissivity doesn't change across wavelengths, like a color-neutral behavior. A diffuse surface means it emits evenly in all directions, no hotspots or beams. Why do we care? Because in practical engineering, you often won't have detailed spectral data. That's where total hemispherical emissivity comes in. It averages everything into a single useful number. Instead of getting stuck in complex spectra, you use this approach to get quick, reliable answers, especially for materials like metals, paints, or insulation materials in real projects.
8. Make the greenhouse effect relatable. The greenhouse effect can sound abstract, but let's make it personal. Think of a car parked in the sun. The glass lets sunlight in, but traps heat, making it hot inside. That's the greenhouse effect in action. Our atmosphere does the same. It lets visible light from the sun enter, but infrared radiation, the heat, gets trapped by gases like CO2 and H2O. This trapped heat causes global warming by building up energy that can't easily escape. Focus on the simple cause-effect chain. Sunlight in, heat trapped, temperature rises. This example helps you connect radiation theory to one of the biggest environmental issues today. 9. Link radiation concepts to real atmosphere behavior. Here's how we apply radiation principles to the real world. The sun sends shortwave radiation, 0.3 to 3 micrometers, that reaches Earth, while our atmosphere absorbs and re-emits long-wave infrared radiation, greater than 3 micrometers. A key number to remember is the solar constant, 1,373 watts per meter squared, which tells you how much solar power hits each square meter of space facing the sun. Finally, we use effective sky temperature to simplify how the sky behaves. Clear skies are colder, around 230 K, and cloudy skies are warmer, around 285 K, because clouds trap more heat. This slide connects theory to everyday effects, why sunny days feel different than cloudy ones, and why understanding radiation helps us predict weather and energy balances. 10. Turn theory into practical engineering insights. Radiation isn't just theory, it's behind many smart engineering solutions. In solar energy systems, we use selective surfaces to absorb more solar energy and waste less heat. In heat exchangers, radiation plays a quiet but crucial role in total heat transfer, especially at high temperatures. Building insulation shows how low emissivity materials, like shiny foils, help keep buildings warm by minimizing radiation loss. Finally, thermal imaging turns radiation into a tool, helping us see temperature differences without contact. The lesson here? Radiation principles help you optimize performance and measure efficiency in real-world systems, making you a more effective engineer. 11. End with a focused, actionable summary. Let's close with what really matters. Radiation is all about energy moving through electromagnetic waves. No material needed. Blackbodies set the gold standard by emitting the maximum energy possible. You've seen how Stefan Boltzmann and Planck's laws help you quantify radiation, while Wien's law shows where peak emission happens. Emissivity, absorptivity, and reflectivity are tied directly to materials. This is where engineering design makes a difference. From greenhouse warming to solar energy, radiation plays a role in big-picture issues and everyday devices. The key takeaway? Mastering radiation properties helps you design more efficient, sustainable systems. Focus on applying these principles to real-world problems. That's where your knowledge will shine.